Well, hello everybody. Welcome to another day of class. Just as a reminder, on Monday we were looking over homework, but we were talking about relations on a set A. And so we're talking about equivalence relations and how those created partitions, and we looked at different ways that that came into play. Today what we're going to do is we're going to talk about another type of relation, but it's going to be instead of a relation on one set A, it's going to be a relation from a set A to a set B. And what we're going to call those are mappings. So what we have is a mapping, which is also known as a function. From a set S to a set T is a relation, which is a subset of S Cartesian product T. And so we're going to call it a rule or a correspondence that assigns each element of S as a uniquely determined element of T. So then we call S the domain and T the domain, codomain, and the range of alpha is all the things that actually get mapped to. So pictorially, what we have is alpha is going to be a subset of S cross T. So for example, if I had something like AB in there, that would mean that if S is my domain and T is my codomain, then because A, B in there, then what's going to happen is if I take A and I follow it under alpha, I'm going to end up at B. So this is our context of function that you would have seen in calculus, but we're going to call it a mapping here. The idea is just, okay, if I have A in my domain, I end up at B in my codomain, and that's what alpha tells me to do, is anytime I see one of these ordered pairs, it tells me how to get from A to B. If I take all the places that all of these things go to, it's going to be some subset of T. So that's what I'm calling my range. So these are all things that actually get mapped to from things over in here. So here's my domain, codomain, and my range. Now notice that because it is a mapping, what I have is if I have AB, I cannot have AC. So if AB is in the set ST and AC is in the set ST, in order to be a function, we'd have to have that B is equal to C. So I would say if this and this are in here, then they have to be the same. So B is equal to C. So that is, as before, we're looking at a relation on from a set to itself. We could have A comma a lot of different things. In particular, we'd have like 1, 1, 1, 2, 1, 3, 1, 4, something like that. And that was okay for relation on a set. And it's okay for a relation on general, but if we want a mapping, we have to have that if we have an A here, we only have one ordered pair where A is here, and then we have a unique element here. So if we want to show that something is a mapping, we have to show that for everything in the domain, there is exactly one thing in the codomain that this thing in the domain gets mapped to it. For some notation purposes then, I'm using alphas instead of f's because that's what we're using in the book, and it's a little more common when referring to them as mappings instead of functions. So that's the notation we're going to stick with. I can write alpha is a mapping from S to T, as the first line there says. So that alpha colon S to T is alpha is a mapping from S to T, or that alpha should be, this alpha should be above it, but alpha is a mapping from S to T. Or I can say something like alpha of X is equal to Y, or I can say X maps to Y. And so that's what each of those actually says as we read them. And so we'll be using those at different times to say things like alpha is a mapping, or it's mapping X to Y. All right. Now, what I want to talk about next is when are two mappings the same, so that we have a formal definition of what a mapping is. We have to know, okay, well, when are two things the same? And so what I'm going to say is that two mappings are the same as if they have the same the same domain And for everything in the domain, alpha of x is equal to beta of x. So if we go back to our picture up here, the idea would be that if I have a beta, it could be a subset of S cross something. It doesn't necessarily have to be T, so let's call it T1. But the idea is that if I pick anything in here, and I map it to here through alpha, I'm going to get the same answer as if I map it to beta. Now the difference is because we don't map to everything in the code, we don't have to map to everything in the codomain. T1 could actually look like this. So we could have different codomains. The important part is we have the same domain, and everything in the domain, the shared domain, gets mapped to exactly the same spot, whether we're using alpha or beta. And that's what we mean by mappings being equal to each other. All right. So I'm actually going to look at this example. And the idea is I want to show or give a proof that either these are the same mapping or they are not the same mapping. So I have alpha is a mapping from z to z, which maps x to x squared minus 1. Beta is a mapping from z to z that maps x to x minus 1 squared. And gamma is a mapping from z to r, which maps x to x minus 1 times x plus 1. So if I want to determine if these are equal, what I'm going to do is just test some numbers and see what happens. So this is going back, we have a theorem basically, is that let's say alpha is equal to beta. We have to test that to determine if it's true or false, and then we have to provide a proof thereof. So if we look at alpha and beta, I would just try something. Well, the first thing I should check is the domain of alpha equal to the domain of beta? And in this case, the domains are both the set of integers, so that those are the same. But the next thing I want to do is just find something like alpha of 0 is 0 squared minus 1, whereas beta of 0 is 0 minus 1 squared. So 0 squared minus 1 is negative 1, whereas negative 1 squared is 1. So what we'll notice is that the first thing I tried here, alpha is not equal to beta. So we would claim alpha is not equal to beta. So we would say our theorem is alpha does not equal beta. Note that 0 is in the shared domain, so I do have to make sure that 0 is in my shared domain, which is the set of integers, but alpha of 0 is equal to negative 1, and beta of 0 is equal to 1, and negative 1 is not equal to 1. So we found one example of where alpha maps something to a different place than beta does. So one example is enough to show they are not equal. Hence, alpha and beta, are not equal mappings. And all we need is one counterexample to show not equal. Alright, then let's look at alpha and gamma. So alpha of gamma, and gamma was x minus 1 times x plus 1. And so in this case, we would get negative 1 times 1 is negative 1. So at least at 0, alpha and gamma are actually equal to the same thing. So that's great. I could try another one, and I'll plug in, say, 1. If I plug in 1, I get 1 squared minus 1 is 0. I plug in 1. I get 1 minus 1 is 0 times 2 is 0. So if I plug in 1, I get the same thing both ways, and it seems like I'm getting the same things out both ways. Now, whether or not that's always true, we have to then prove, but at least the first couple examples make us believe that these are actually going to be the same thing. So that means for our proof, we're going to gear it towards let's show that they are equal. So our theorem is alpha is equal to gamma. Now, I do need to point out that in order for them to be the same function or the same mapping, they have to have the same domain, and they have to have that everything gets mapped to the same point. So first, I want to look at the domain of alpha and gamma as given to us, and notice that alpha is a mapping from z to z, and gamma is a mapping from z to r. So the domain, and I can write it as the domain of alpha is equal to z is equal to the domain of gamma. Therefore, we have that the two domains are equal because they're both equal to the set of integers. So they have a shared domain. Furthermore, now what I have to do is let's say x be in the shared domain, the set of integers. Then I have to show that alpha of x is equal to gamma of x. And so I'll write that down here. That's my goal. I have to show alpha of x is equal to gamma of x. So I'm just going to start off on one side and say alpha of x is equal to x squared minus 1. Now, as I have been doing in this class, I kind of like to start with both sides. So I'm starting on the left, I'm starting on the right here at the bottom. I'm not claiming these are equal until I get something that is equal, but I'm going to kind of work my way backwards and forwards until I get this. And the idea is that I know that this is equal to x minus 1 times x plus 1. Well, if you don't see that those are equal, what I could do is multiply these out, and I get x squared plus x minus x plus 1. And so now if I'm working this direction, I get x squared plus x minus x is 0 plus, minus 1. Negative 1 times positive 1 is negative 1. So if I simplify this, I clearly get x squared minus 1. And what I end up with is alpha of x is x squared minus 1 is equal to x squared plus x minus 1, which then becomes x minus 1 times x plus 1, which is gamma of x. Hence, alpha of x is equal to gamma of x for all x in their shared domain, which is a set of integers. So we would say these two mappings are the same. I do want to point out that we've proven they're the same, but if we look at alpha, the codomain is actually the set of integers, whereas for gamma, the codomain is the set of real numbers. Therefore, even though the codomains are different, these are still the same function. We're not worried about if the codomains are the same, just the domains have to be the same, and then everything has to get mapped to the same point, and that would mean that the range is the same, because everything is getting mapped to the same things, but we could map into a larger set if we wanted to and still call it the same function. Alright, now I just want to point out we showed alpha and gamma were equal, and alpha is not equal to beta. Therefore, we would know that gamma is not equal to beta. And so checking any of the pairs we get just from showing those two. So we would try alpha, gamma. We know beta is not equal to gamma because gamma is equal to alpha, which is not equal to beta. All right. And again, just some more definitions we're setting up here to make sure that we understand or have a base to start from is one mapping that we're going to talk about a lot is the identity mapping. And the identity mapping we're going to call iota. And what iota is the mapping from S to S that just sends x to itself. So that just means iota of x is equal to x. And so if we were to picture this, what we would end up with is that we're going to start off in our domain, And the idea is that through iota, we just end up where we start. So x gets mapped back to s. Sorry, x. So x gets mapped back to s. And so we're mapping our domain to itself. So it's both our domain and our codomain. And that's what we mean by the identity mapping. And we denote it as iota, or if we don't know what the domain is, because if I change the domain, this is a different function. So I can have iota sub the real numbers, or iota sub the integers. And these two would not be the same function because they have different domains. So since they have different domains, they're different functions. But I would say this is the identity on the set of real numbers, this is the identity on the set of integers, and we can have an identity mapping on any set. And if we don't know what set if it's not clear what set we're talking about, instead of just writing iota, we'll put a little subscript here to tell us what our domain is. Alright, now that we kind of have it set up is when are two mappings the same, what we have an identity mapping to talk about, and what I want to say here is that we also have different properties we're going to look at. If we recall our equivalence relations, we said, oh, well, a relation could be reflexive, symmetric, and transitive, and those were things that we checked. When we're talking about mappings, well, we first have to check that it's a mapping, so it's well defined. So for every A in the domain, there's exactly one B in the codomain type of thing. But another property we would have is onto. And what does onto mean? Well, it means that if alpha is a mapping from S to T, then alpha of S is equal to T. So that's saying that the image of the mapping is equal to the entire codomain. So if I go back to pictorially drawing onto, our original picture of a mapping was S to T. This was my domain and my codomain, and we said, okay, here is the stuff that actually gets mapped to as a range. So if it's going to be onto, what we're saying is that basically there can't be anything in here, so that the range is equal to the codomain, so there's nothing left over. Therefore, everything in the codomain gets mapped to something from here. So it would say is for all y in the codomain, there exists an x in the domain with alpha of x equal to y. So this would be another way to say onto, is that for everything in the codomain, we can find something in the domain that gets mapped to it. Or that is, the image is equal to the codomain. So everything gets mapped to, and that is an onto function. And notice I'm using the word mapping and function here interchangeably because based on your context, both words do mean the same thing. It's just sometimes people prefer functions, sometimes people prefer mappings. I just have both in my head, so I'm kind of switching back and forth. Alright, so now let's work with the proof then based on onto. So let's suppose that alpha is a mapping from R to R. Can we show that x to x squared is not onto? Well, if we look at what we've done at the chalkboard already, what we have is that a mapping is onto if for everything in the codomain there exists something in the domain that gets mapped to it. So if we want to show something is not onto, we have to negate this statement. So to negate this statement, we would get, instead of for all there exists a y in the codomain, such that for all x, we have that alpha of x is not equal to y. So I just negated the statement, but the idea would be that there exists a y such that for all x in my domain, alpha of x is not equal to alpha of y, so that is we never get the picture that x is mapped to y. So this cannot happen. And so if we want to show something is not onto, what we have to do is we have to find a y that never gets mapped to. Alright. So what I have here is I'm mapping the real numbers to the real numbers, where x is mapped to x squared. And if I want to show that's not onto, I have to find something that is not in the range. So now notice that, let's just think about what is in the range. Well, notice that 1 squared is 1, so since 1 squared is 1, 1 is in the range. 2 squared is 4, so 4 is in the range. 1.1 squared is 1.21. Hopefully I did that correctly, otherwise you have it in video evidence that I don't know how to multiply, which would be really embarrassing. Alright, I'm going to leave it up there. But the idea then is 1.21 is indeed in the range. And so if I think about the range, I have to think about all the numbers that are in the range, and it seems like there are a lot of numbers in the range because there are. And so actually, if I draw this, I can think of this pictorially as I'm going to map from the real numbers to the real numbers. So I could say here's my x and here's my y. And so as a relationship or a subset of r squared, because remember a mapping is a subset of r squared, we could graph that, and it's just going to be all the points where y is equal to x squared. So we're going to have all the points x comma x squared. It's going to look like that. So, is there something that doesn't get mapped to? Well, if we look at our picture, it becomes clear that any negative number would work here. So for example, -1. So what we can do is show that nothing gets mapped to -1. So what we would do for our proof is note that -1 is in the codomain, which is the set of real numbers. Furthermore, if x squared is equal to -1, then x is equal to the positive negative square root of -1. But we can't take the square root of a negative number and remain a real number. We would end up being a complex number. So x is not a real number. Therefore, there are no real x such that alpha of x is equal to -1. Hence, alpha is not onto. Now, I am being a little bit more formal here because I really want to explain what's really happening. Is the idea is if I pick -1 and I tried to find something that was equal to it, I get a contradiction here because I would then be taking the square root of a negative number, which is not real. So therefore, we get that this cannot be onto. What it would suffice to say is that for a proof from you guys, what I'm looking for is that I would need you to find this number. So note that -1 is a real number, and there is no real number such that x squared is equal to -1. So if you jump down to this, there is no real x such that x squared is equal to -1. That would suffice for a proof from you guys, but I really wanted to be precise here just to say why that's true, is because we end up with basically doing a proof by contradiction here. We assume that there would be one, showed that it can't be real, therefore we have a contradiction. Alright. Do you guys have any questions on that? If not, then how about we show a mapping is onto? So how would we show that a mapping is onto? Is, well, we'd have to show for every y in the codomain there's something that gets mapped to it. So here what I have is alpha of x is equal to x cubed, And I want to show that this is onto for when I'm mapping the set of real numbers to the set of real numbers. So what would my proof look like is I would pick something in the codomain, and now I want this to work for everything in the codomain, so I'm just going to let y be an arbitrary thing in the codomain. I can't say pick -1 or 5 because my proof's only going to work for one number. I have to show this is true for all y in the codomain, so I'm just going to let this be an arbitrary y in the codomain. Now I have to find something that gets mapped to it. So what I would do off to the side is say, well, I want to find an x such that alpha of x is equal to y. That is, x cubed is equal to y. And so if I want x cubed to be equal to y, what I'm just going to do is solve for x in terms of y. So x is going to be the cube root of y. So I know that if I take the cube root and plug it into the function, I'm going to get out y. So the only thing to be careful of here is that if I take an arbitrary real number, can I always take the cube root? Well, the domain of an odd root is all real numbers. So therefore we can say, note that x equals the cube root of y is a real number because you can always take the cube root. Also, now we have to show that this x gets mapped to this y. So alpha of x is equal to x cubed is equal to the cube root of y cubed is equal to the cube root cubed cancels out, and we just get y. Hence, alpha is onto. So because we let y be arbitrary, this is going to work for any real number y. Therefore, we can always find an x, namely the cube root of y, which gets mapped to y. So the x cubed will indeed be an onto mapping. So x squared would not be onto, but x cubed would be onto. And so we have now proven that to be the case by walking through these proofs. All right. So now, as well as onto, we can also talk about one-to-one. So what does it mean for a mapping to be one-to-one? Well, the formal definition, if mapping or alpha is a mapping from S to T, it's going to be one-to-one if I take two different things in the domain, then their images have to be different. So if x1 is not equal to x2, that implies that alpha of x1 is not equal to alpha of x2. So if I look at the board and I try to draw a picture of one-to-one, what I get is here's my domain, here's my codomain. So if I start off with two different points, I have to end up at two different points. So this is not equal to this, so under alpha, they each get mapped to their own spot. So what we're really saying is that we can't have this picture. So if we ever have two different points going to the same point under alpha, this would not be one-to-one. But if it's always the case that I'm going to end up at two different spots when I start at two different spots, I would be one-to-one. All right. Now I do want to point out that our definition of one-to-one is if x1 is not equal to x2, then alpha of x1 is not equal to alpha of x2. And so if we want to prove that something is a one-to-one, I'd have to show that whenever x1 is not equal to x2, alpha of x1 is not equal to alpha of x2. Now, if we remember to our proofs, we've done quite a few now, but whenever we had not equals, it made it very difficult to do a proof because it was hard to find a place to start. So if I tried to prove this as an if-then, notice that I'd have to deal with a lot with not equals. So instead of doing a direct proof here, what we could do is a proof by contrapositive, and we could say this is equivalent to saying if I'm going to negate this statement, so that would be x1 is equal to alpha of x2, then, so I'm switching the order and negating the statement, so instead of x1 not equal to x2, then we get x1 is equal to x2. So when we're showing one-to-one, instead of working with this formal direct definition, we normally work with the contrapositive. And we say that, well, if alpha of x1 is equal to alpha of x2, then x1 is equal to x2. That means that our mappings is indeed one-to-one. And so what we can do here is we can assume that the images are the same. We have to show x1 is equal to x2, and we get that our mapping is one-to-one. All right. So I have two different examples here. I want to show x to x plus 1 is one-to-one, and I want to show x to x squared plus 1 is not one-to-one. So I'm going to graph x plus 1. So if we remember back to calculus, if we're going to graph a function, we said that it was one-to-one if it passes the horizontal line test. And that's because for every y, there is only one x that gets mapped to that y. So if two things got mapped to this point right here, well, they'd have to be the same. They'd have to be whatever point this is. So if I look at x plus 1, it seems to pass the horizontal line test. So it seems that for every y, there's exactly one x that gets mapped to it. So it looks like this is indeed a one-to-one mapping. But now to prove that, what we have to do is, so x maps to x plus 1 is one-to-one, which I'm just going to write as 1 dash 1 is a shorthand way to write one-to-one. And my proof is going to look like, let x1 and x2 be in the domain, which in this case is a set of real numbers, with alpha of x1 equal to alpha of x2. So we assume that the images are the same, and what we have to do is show that then x1 is equal to x2. So just to remind us, I'm setting this up. I assume this, I showed this. So now I have to get from here to here. So I'm going to do the definitions is, well, alpha of x1 is x1 plus 1, then is equal to x2 plus 1. Well, since x1 plus 1 is equal to x2 plus 1, I can subtract 1 from both sides and just get x1 is equal to x2. And so really this wasn't that bad of a proof. We just had to say assume that these are equal. Well, that means x1 plus 1 is equal to x2 plus 1. I subtract 1. That shows that I had to start in the same point. Therefore, if the images are the same, the original point had to be the same. So this is indeed a one-to-one mapping. All right. Now I'm going to go back to if it is one-to-one, then if x1 is not equal to x2, then alpha of x1 is not equal to alpha of x2. If we want to show something is not one-to-one, what we have to do is prove the negation of this. So what is the negation going to be is we have x1 is not equal to x2. So the negation of if p then q is p and not q. So we have to find x1 is not x to x2. So this is an implied for all. So there exists an x1 and x2 such that alpha of x1 is equal to alpha of x2. So I'm going back to my logic to say, okay, if I need to disprove this, I have to prove the negation. So that means that instead of for all, if we get there exists an x1 and x2 where they're not equal, but the images are. So if I keep that in mind and work with x is mapped to x squared, the point is I just have to find two distinct things that get mapped to the same point. This one's not too bad. I just picked a positive and negative of the same number, so -1 and +1, I get a counterexample. So I would say note, -1 and 1 are in the set of real numbers, which is my domain. Also, we get that alpha of -1 is equal to -1 squared is equal to 1 is equal to 1 squared is equal to alpha of 1. So we get alpha of -1 is transitively equal to alpha of 1. Hence, we started off at two different points and ended up at the same point. So alpha is not 1, 2, 1. So there's an example of how to show a function is onto or isn't onto, is 1-to-1 or isn't 1-to-1. And so we can go through different examples of different mappings to see, are they 1-to-1, are they onto, are they not? Just like when we were talking about relations, we talked about, is this reflexive, is this symmetric, is this transitive? And so we can do similar types of proofs, proving properties for different mappings. All right. Before, I feel like that's enough for today. I know we still have about 10 minutes left, but I feel like if I start this one, it's going to go longer than the, 14 minutes we have left. So I'm going to actually go ahead and let you guys go there and say, we'll start looking at the homework from this section, or at least the first one or two, and say, well, what is a mapping? What does it mean to be 1-to-1? What does it mean to be onto? So start kind of processing that over. On Friday, we'll talk some more about mappings. We'll talk about different types of mappings and different things that they can have. So, thank you for joining me, and I will see you on Friday.